Hey there, calc folks, back here with another video in my lecture series here on, well, what are we looking at? Multivariable functions. We've just introduced ourselves to partial differentiation and the chain rules for multivariable functions. What we want to start looking at now is a little bit of application. All right. One application we're going to see here for our partial variable calculations is that it's going to give us an alternative way to go about performing what we think of as being that process of implicit differentiation that we saw back in Calculus 1. All right. And if you remember that process of implicit differentiation seen back in Calculus 1, that was a bit of a tedious process. That certainly back in Calc 1 was a little unsteady in its process, right? You certainly didn't feel rather intuitive at times. It was a mix of theory with calculation, right? And like I said, could be a bit of a tedious task at times. Whereas what we're going to see here is an alternative, folks, to that implicit differentiation that we saw back in Calculus 1. All right. We are going to look at implicit differentiation, all right, of multivariable equations. All right. One thing I'm going to do real quick. I didn't do this on this. Quick little spell check just to make sure all my spelling was right. Didn't remember if I ran that on that or not. Let's flip over here. What we're looking at. We are looking at implicit differentiation. Right. This topic known as implicit differentiation of multivariable equations. Now this is implicit relationships between two variables in an equation. Right, is what we're looking at in this technique. Now, there is an analogous for implicit partial differentiation, which we'll see develop at the end here. Right, but this is really what we're looking at is multivariable equations with two variables to begin with, x and y. Right. Consider what is up with my lights. Not shifting color throughout. Let me get that right. All right. So, what we begin with here is considering an implicit relationship between x and y. Remember, what's an implicit relationship is not a relationship that explicitly states one variable in the context of the other. Right? It's not explicitly a functional relationship. Right? And it can't necessarily be explicitly expressed in a functional relationship where one variable depends upon the other functionally. Right? This is what we call more of an implicit relationship. Right? Where we do have a relationship between x and y, which is certainly described by some equation, but it's not explicit. It doesn't tell you one variable explicitly in terms of another. All right? Well, what we can do here what we note is, suppose we have this implicit relationship between x and y described by this notation seen here. And this is going to be something we're going to be able to do with our equations in the context of multivariable functions. What I am doing here, right, we are assuming, in a sense, that our relationship between x and y is a level curve for a higher dimensional surface. A higher dimensional surface we define by the multivariable function big F of x comma y. Right? Big F of x comma y set equal to 0 would be an equation involving two variables, x and y, where that two-variable equation set equal to 0, or that two-variable expression set equal to 0, to make that two-variable equation, would represent a level curve for that higher dimensional surface, big F, of x comma y. Right? So what we're considering here is having an implicit relationship between x and y described by this. Now, when we see this, this is known as a level curve for a higher dimensional surface. All right? So, with a relationship described in this manner, defined the derivative of y with respect to x for this implicit relationship, we first assume y is equal to f of x, implying that this implicit relationship can be expressed in this manner seen here, right? Still as this level curve, but now strictly in terms of x, where we're assuming y is equal to f of x and substituting in f of x, right? Where from here we can now apply the derivative operator to both sides, right? Applying the derivative operator to the left-hand side will give us this result here, whereas applying the derivative operator to the right-hand side will give us this result seen here. And on the right-hand side, that result is going to be equal to 0. Right? Whereas from what we might think of as being chain rule 1 of multivariable functions, the derivative with respect to x for that implicit expression described by f of x comma f of x would all be described by this right-hand side. It would be the partial of big F with respect to x times the derivative of x with respect to x, plus the partial of f with respect to little f times the derivative of f with respect to little x. Right? F taking the place of y in this relationship, right? In this description, under these assumptions. Right? Where from that, those two results for derivatives, right? Now, for the derivative of f with respect to x, which is also known as dy dx, for y equal to f of x. Now f dx equals dy dx for y equal to f of x. And it follows then that the derivative with respect to x for big F of x comma little f of x, which would be equal to the derivative with respect to x for 0, implies this result seen down here, where you'll notice the first of all that value there does not change. However, it does involve this differential dx divided by dx. Any value divided by itself will always equal 1 as long as we're not dividing by 0. All right? Whereas over here, what I've done is gone back in and replaced my f with the value of y, because y is equal to f of x. Note for this, note now this for, we might say here, the assumed value of y equal to f of x. It follows this, implies this. That's probably a best way to say that. So let me make those corrections. All right. Or, like I said, since dx is equal to 1, we could actually make this statement here. Where notice, in this statement here, or either one of these two statements, we have a dy dx. The dy dx, the derivative of y with respect to x that we're seeking to describe for this implicit relationship. Solving for that dy dx, I would first subtract this partial of big F with respect to x from both sides, and then I would divide by this big partial of big F with respect to y. that would produce this result. All right. Solving for dy dx, right, we end up with the opposite of the partial of f with respect to x divided by the partial of f with respect to, this should be y. Right. Which we might think of as really just the opposite of big F's partial with respect to x divided by big F's partial with respect to y for an implicit relationship defined as this level curve, where big F of x comma y describes that what? Describes that expression, right, seen in our level curve set equal to 0. Right? This here is our new formulation. If we can write an explicit or an implicit relationship set equal to 0, this also works for explicits, but we're considering the case for implicit. If we can take an implicit relationship and set it equal to 0, what we will see defined on the other side will be big F with respect to both variables x and y. It'll be a multivariable equation involving both x and y. All right? Where I can find the partials of big F with respect to x, and I can find the partials of big F with respect to y. And when I take the opposite of big F's partial with respect to x over big F's partial with respect to y, I end up with the derivative of y with respect to x in that implicit relationship. And yes, the order is proper here, folks. This is the biggest mistake students make, is they think it's big F of y over big F of x. It isn't. It is big F of x over big F of y. We just showed that here with this proof. Right? You are going to subtract this from both sides and then divide by this. The subtraction is what produces the negative of this. And then when you divide by that, that's going to move to the denominator. And then what you will notice, this is just big F of x. This is just big F sub y. Big F sub x, big F sub y. The partial of big F with respect to x divided by the partial of big F with respect to y. Its opposite value. All right. Let's look at an example. This is a quick set of notes, folks. All right. This becomes a convenient way to calculate dy dx for both I should really say here, just implicit relationships between x and y. Right? Here's an implicit relationship between x and y, and we're being asked to find dy dx. Consider dy dx for this implicit relationship. Now that is a multivariable equation. Equation involves variables x and y, where it is not solved explicitly for one variable or the other. So describing dy dx using traditional methods is not going to be the best approach. What we're going to have to use here is a little implicit differentiation. And we could go back to our Calc 1 methods to perform that implicit differentiation, but we just learned a technique seen above. If we can set this equal to 0, what we define is a level curve for a multivariable function called big F. And that is exactly what we do here, folks. We subtract from both sides that quantity y plus 2 cubed. Right? Subtracting y plus 2 cubed from both sides, right, defines this relationship, this implicit relationship, as this level curve, big F of x comma y equal to 0, where big F of x comma y would be equal to x squared times y minus 1 quantity squared minus that quantity y plus 2 cubed in value, all set equal to 0. But big F of x comma y would now be defined as this statement seen here. Where with that statement seen there, you can find your partials with respect to x and y rather readily. With respect to x, This is all a constant, so that will zero away. Here's our only factor in the first term with respect to x, and its derivative would be 2x times this constant y minus 1 squared. So with respect to x, the partial of big F would be 2x times y minus 1 squared. Whereas with respect to y, it would be the partial of this first term, which would be 2x squared y minus 1, minus the partial of the second term with respect to y, which would be 3 times y plus 2 quantity squared. There is a little chain rule happening in all of that, folks. Right? And notice that is the result we see down below. For big F of x comma y defined by this left-hand side, right, this equation set equal to 0, the expression we would have when we set this equation equal to 0 on the left-hand side, right? The partial of big F with respect to x would be given by this quantity seen here, and the partial of big F with respect to y would be given by this quantity seen here. So what would be the derivative of y with respect to x? It would be the opposite of this over this in value, implying that dy dx would be equal to this statement here. The opposite of f's partial with respect to x over big F's partial with respect to y. Right? That is implicit differentiation done now in the context of multivariable functions. We can take any multivariable equation with any number of variables and set it equal to 0, and what you end up describing is a level curve for a higher dimensional function, for a function that exists one dimension higher, right, than the dimension described by the multivariable equation. It's kind of a neat connection to make, and it's going to be a connection we actually exploit when we get over into the idea of tangent planes. Right? Every implicit or explicit equation in one dimension of space, or in n-dimensional space, can be described as a level curve by setting it equal to 0, right, for a higher dimensional functional behavior, that will exist in n+1 space. Right? That will always be true. And we're going to exploit that fact, folks. Now, we do see an analogous idea here for partials. Right? Note, this technique can also be used to calculate partial derivatives for implicit relationships between, as I said, x, y, and z in three-dimensional space. If an implicit relationship in 3 dimensions is expressed as the level curve seen here for what is this is a relationship in 3 dimensions, this is going to be a level curve for a 4-dimensional surface. F of x, y, z is actually a surface that exists in 4 dimensions. Right? The output f for those inputs x, y, and z, that's 4 dimensions. When we take that 4-dimensional level curve and set it equal to 0, we have an equation in 3 dimensions. And that equation in 3 dimensions is a level curve for that 4-dimensional surface. Well, if we do something similar to what we've done above and express that 3-dimensional equation as a 4-dimensional level curve, right, or the level curve for a 4-dimensional surface, it would be a level curve in 3 dimensions. Then the partial of z with respect to x would be the opposite of f's partial with respect to x over f's partial with respect to z. And the partial of z with respect to y would be equal to the opposite of f's partial with respect to y over f's partial with respect to z. All right? We see a very analogous technique to what we've defined above. Now consider the unit sphere. Here's an example. Consider the unit sphere defined by x squared plus y squared plus z squared equal to 1. The unit sphere, a sphere one-dimensional in radius, centered at the origin of a three-dimensional system, right, does not describe functional behavior. Its upper hemisphere does and its lower hemisphere does, but collectively that entire sphere does not describe functional behavior. It's just a multivariable equation that exists in 3 dimensions, seen there in our notes. Right? However, this multivariable equation seen in 3 dimensions that describes this unit sphere is really just a level curve for some higher dimensional surface. Right? For some surface we can't visualize. Right? This 3-dimensional equation is just a level curve for a higher dimensional surface. And we can actually define that surface as big F if we set this equal to 0 by just subtracting 1 on both sides. We would define big F in terms of x, y, and z. Right? Defining this equation as the level curve big F of x, y, z equal to x squared plus y squared plus z squared minus 1 equal to 0. Right? Implies that big F's partial with respect to x would just be 2x. Big F's partial with respect to y would just be 2y. And big F's partial with respect to z would just be 2z. So in this case, our implicit derivatives, our implicit partial differentiation, right? The implicit partial derivatives of z with respect to x and y are given as follows. Right. And what we would have here is the partial of z with respect to x would be negative x over z, and the partial of z with respect to y would be negative y over z in value. Right. And that would describe the rate of change, right, as we understood partial derivatives on the unit sphere. The rate of change on the unit sphere where y is held constant and only x is allowed to change. That's the partial of z with respect to x. Or where x is held constant and only y is allowed to change. That would be the partial of z with respect to y. Right. However, noting those two partial derivatives, we're going to later find out as we can use that information to calculate the derivative actually in any direction at any point on our unit sphere. Right. Calculate what we call a directional derivative. All right. But yeah, this is implicit differentiation, folks. It's 25 minutes in. This is a short set of notes. It's a quick topic. A couple of examples. All right. Along with some proof. It does start off with the proof up here, folks. If you want to go, where does this formula all come from? Is it really big F of x over big F of y? Well, it's all right there in the proof. Yes, it is. All right. What we have down below here is example. I do calculate these first partials of this big F rather readily, but it is really not a tough calculation once you put in a little bit of practice there, folks, and understand what those partial calculations are. And then it is nothing more than arranging it into a ratio with this quantity over this quantity, right? And then take its opposite. Right? With this idea, all extending into three-dimensional space, right? For partials of z equal to f of x comma y, or what we should say is implicit cases are relationships between the three variables x, y, and z. Right? And again, it all exploits this idea that every curve in two dimensions, right? If I was to just draw a line on a paper, circle any curve in two dimensions, right? Those are always level curves for three-dimensional functional surfaces. And any three-dimensional surface doesn't have to be functional, right? Just like the curve didn't have to be functional, right? Describes a level curve for a four-dimensional hypersurface. And every four-dimensional hypersurface describes a level curve for a five-dimensional functional surface, hypersurface, right? And up the line. Right? We exploit that fact to calculate these implicit derivatives. All right, folks, with that said, I'm going to end the video. Like I said, we're at the 25-minute mark, and I want to try to keep this one brief. I do have another one to get out to you here, covering the gradient. We will, let me try to get into that one next here. So I'll have that up shortly. But I'll end this one. I'm going to follow up with the next section of material, which is going to kind of look at the gradient, and then directional derivatives is where we're heading. We're going to finish up then with tangent planes and max and min problems. Right. Lagrangian multipliers we will see if we have the time for. Those do take a little bit of time, and we only meet twice a week, and this COVID just has our time all wrapped up already. So that's kind of hard to see if we want to try to fit that in somehow. All right. But I hope you're all doing well. I hope you're hanging in there. And I'll see you in class. Catch you next time.